So we're going to look at electric field strength, or in the beginning I said intensity. So electric field intensity E, or electric field strength E. So if we place a positive test charge, we call it QT, in the locality of other electric charge at some point P, based on what we have studied earlier on, Coulombs law, we know that this charge QT will experience a force Ft, because if you have one charge, you put another charge QT there, then this charge will have a force, like we said just now, Coulombs law, Q1, Q2 over 4 pi epsilon r squared. And then we simply define the electric field as the force Ft divided by the test charge magnitude Qt. And then we said that the electric field E equals to F over Q in the limit of Qt going to 0. So what it means is that the limits of Qt going to 0 means that we want the test charge to be very small. Okay, so it has to be very small so that it doesn't disturb the systems. Because if you know that if I have a charge here, I put a Q charge very strong here, then this both will experience a force. So this will move. Okay, so if physically I really move, I put a charge here, then this actually will go away. Okay, because of the force. So we want to put a charge here that doesn't disturb the system. So that's why you said Qt has to be negligibly small. So small that it doesn't disturb the system. So that is the definitions, but it doesn't really help you to perform calculations using this particular definitions. Okay, so it's not very helpful definition, the one that I showed just now. So it will be easier if you can think of it, if I put a charge to be 1 coulombs, my test charge Qt to be 1 coulombs in the system, then going back to these equations, if I put Qt equals to 1 coulombs, then my electric field simply equals to that force. Okay, because then my E will be equals to Ft, because Qt is 1 coulombs. But in the real system, if you put a 1 coulombs there, as I mentioned very early on, 1 coulombs is a very large charge. So if I put 1 coulombs there, then everything else will go away, because of that charge will cause a huge disturbance to the system. But mathematically, this is the right thing to do, because mathematically, if I put 1 coulombs, then I can work out the electric field simply equals to the force experienced by that 1 coulombs charge. So for calculation wise, this will be a much better definition. So said that the electric field at some point P is equals to the force of a unit positive charge placed at that point. Okay, so this is the definition that we're going to use for calculations. Okay, to work out the electric field. So physically doesn't make sense, because that says that 1 coulomb charge will perturb the systems, but mathematically it makes sense. So we can write down our force will be equals to Q times the electric field. And then by definition, the direction of the electric field at any point is the direction of the force of a plus charge placed at that point. Okay, so the electric field E is in the same direction of the force experienced by this charge if this charge is positive. Okay, so if my Q is equals to 1 coulombs positive, then we have F, or my E will be equals to my F, and they are in the same direction. Okay. So that is the electric field, or in other words, we can set that electric field. So earlier on we have F equals to Q1, Q2, 4 pi epsilon naught R squared unit vector R. Okay, so F2. So if I divide this by FQ2, then I get my electric field. Okay, so that is my electric field Q over 4 pi epsilon naught R squared, my unit vector R. Okay, so that is what I have just explained just now. So my electric field will be Q over 4 pi epsilon naught R squared unit vector R. So if I use back my previous example, if I said this is Q1, this is Q2, so normally this will be my force F2. So my E field at that point will be F2 divided by Q2, and that will be equals to Q1 over 4 pi epsilon naught R squared unit vector R. Okay, so we define this as plus Q, or Q1, here is Q1, here is just Q. Okay, so this is how these equations come about. Okay, so very similar equations to your Coulomb's law. So electric field, except we drop one of the Q, one of the charge. Okay, we make one of the charge to be 1 coulombs mathematically, and therefore we have the electric field. So my electric field will be in the same directions as my unit vector R. So it's pointing radially outwards in the directions of the unit vector R. Okay, the units for electric field, that will be watts per meter. But from our definition, you can also set that the unit is newtons per coulombs. This is more widely used. Okay. Okay, so the electric field is the other inverse square law. So meaning that if you move further away from the charge, the electric field also decay by square of the distance. If a system has more than one charge, then the electric field at any point is the vector sum of all the individual electric field at that point due to each individual charge. Okay, so meaning that if I have Q1, Q2, if I want to work out the electric field at this point here, P, then I define one vector, R2, one vector, R1, then I can work out my E field, E2, E1, then I do a vector sum of E1 and E2. Then I work out the final or the net electric field experienced at point P. Okay, so I have two vector, E1, E2. I'm sure you know how to sum up vector. So this will be my vector E. Okay, so if more than one or two, if you have more, if you have 2, 3, 4, so it's just a sum of all electric field in vector. Okay, example. Find the electric field E at the origin due to a charge of 5 nanocoulombs at position vector 111 and a charge of 2 nanocoulombs at 100 centimeter. So we have one charge Q1, 5 nanocoulombs at a position vector of 111. And then we have one charge Q2, 2 nanocoulombs at position vector 100. And then you're asked to work out what is the electric field at the origin. Okay, so you need to work out the individual electric field. So if this is a positive charge, so pointing towards my origin, at this point here, you have an electric field E2. Okay, so if I define this is my position vector pointing at the origin, and that vector will be minus R2. And then my electric field will be pointing in this direction, E2. And again, this side, if this is also a positive charge, then I define this is my vector, and this vector will be minus R1. And then my E field will be pointing in this direction. And then you work out E1 and E2, then you can do the vector sum of that two vector, and then you get the total electric field at the origin. So if I define this as my vector R1, then this R1 will be negative of 1, 1, 1 vector. Similarly, if I define this as R2, this will be negative of 1, 0, 0. Okay, so 1, 0, 0 is from the origin pointing to Q2. So if I take from Q2 pointing to the origin, that will be negative of 1, 0, 0. Similarly for R1, from origin pointing to R1, that will be 1, 1, 1. So now I want the vector to be from the positive charge or from my Q1 pointing to the origin, that will be minus 1, 1, 1. And then you can define your electric field. E1 will be equals to Q1 over 4 pi epsilon naught R1 squared times the unit vector R1. And then you define R2 as Q2 over 4 pi epsilon naught R2 squared over unit vector R2. So we define R1 as minus 1, 1, 1. Then therefore the magnitude of that will be square root of 1 squared plus 1 squared plus 1 squared. That will be square root of 3. Unit vector will be my vector R1 divided by the magnitude, which is root 3. And then R2, that will be minus 1, 0, 0 centimeter. Magnitude will be 1 centimeter. And then unit vector will be minus 1, 0, 0. Okay, unit vector doesn't have units, okay, because you have centimeter divided by centimeter. So top, the vector is in centimeter, the magnitude is in centimeter. So if you put in that value, you can calculate E1, E2 in vector, then you simply do the vector sum of E1 and E2. So my total electric field will be E1 plus E2. Okay, so if you put in the value, the electric field magnitude E1 is 1.5 times 10 to the 5 watts per meter. And then Q2 will be 1.8 times 10 to the 5 watts per meter. And then put in the vector. So that is my electric field E1, E2, and then you can do a vector sum of these two. And that is your solution for the total electric field. Okay. Any questions on this? Do you understand or you don't understand? Anything you want me to repeat or explain? So it's all vector, okay? All vector sum and a bit of vector calculation. So you need to know how to define directions of vectors, unit vectors, and then use them in the calculations. I think it just, I don't think it's, you don't understand. It's just maybe the way I present it is not the normal way you used to do it, I guess. So it's the same thing. I mean, this, for example, this vector sum here is just the sum of these two equations. I mean, in your maths, you most likely studied, let's say, A equals to 2i plus 3j, let's say two-dimensional. And then B is equals to, let's say, 1 or I plus 4j. So if I want to calculate the sum of A plus B, I'm sure you know how to calculate this, right? So this is 2i plus 3j plus I plus 4j. And this is equals to 3i plus 7j, right? I'm sure everyone knows this. Yeah. So all I have done is I make this equals to 2, 3, 1, 4. Just to make life easier. No need to write I and j or unit vector. And now my sum, A plus B, will be just 2, 3 plus 1, 4. And just x plus x, y plus y. As simple as that. Yeah. And that will be the same as your 3i plus 7j. Okay. So similarly here, I have I, j, k. And then here is I, j, k. So it's just x plus x, y plus y, j plus j, and give me my total vector sum. Okay. So difference is that here is in two-dimensional, and now we're working in free space, is three-dimensional. But there are three directions, x, y, and z. So you just have to add them up independently, x plus x, y plus y, z plus z. And then the magnitudes of it will be square root of x plus square root of y plus square root of z, and take the root of that. That gives you the magnitude. Is that okay? Is that clear or still no, not following? Okay, clear? Good. Okay, so there's the calculation of the electric field. Pictorial of electric field. We want to be able to draw electric field. So electric field is a vector. We know that electric field is a vector field, magnitudes and positions. But electric field magnitude and position changes as we move through space. Okay, I'm sure you learn how to draw magnetic field, north, south, and we always draw it like that. Correct? And then closer we draw more lines, and as it go further we draw wider line. Yeah, you learn that? Okay. So same thing, magnetic field is also a vector. Any idea why you draw more line here, less line further away? It's the strength, yeah? So closer to the magnet, the strength is stronger, we draw more lines. Further away, the strength decrease, we draw less lines. So it's the same thing with electric field. So we don't draw it the same way as we draw vector, but we draw it. So in vector, the length of vector arrow tell us the magnitudes of the vector. Okay, so in vector, we said that this line here, how long this line tells you the magnitude. But in electric field, the arrow only tells you the directions of the electric field. Okay. The strength of the magnitudes, it depends on how far apart the line you draw, just like how you learn it in magnet. Okay, when you draw more lines, it shows that the magnitude is stronger at that point. If you draw less line, you know that the electric field or the field is lower in magnitude at that point. The same thing with electric field. Okay, there are somewhat difference between the electric field, how we draw it, compared to a vector. Although electric field is a vector, but we don't draw it the same way as we draw vector. Parallel lines in some region indicates a uniform field magnitudes and directions. Okay, so meaning that if I draw parallel with same distance apart, so we said that the field is parallel in that region. If we have a diverging or converging field, meaning that if I have field like that, or field like that, so we know that here, somewhere around here, is most likely has a source that giving out electric field. Somewhere around here, we have a sink that the electric field actually going into it. Okay, something like this, uniform. So here, more compact lines. This region has a higher field, higher electric field. Here, less compact, has a lower electric field. Relative comparison from one to the other. Okay, so not in isolation, so you can't just look at the field in isolation and say that here has a higher field. You have to compare between two regions. Okay, here is a diverging, the field is going outwards. So we have a source there, we have a positive charge. We know that positive charge, the electric field is pointing away from the positive charge. So how do we know that? We said that electric field, we can test it. If I put a positive 1 Coulomb charge here, what will happen to that charge? It will go away from the positive charge because we know positive charge and positive charge is repel. So if I put a test charge of 1 Coulomb, we know that this will have a force that going in this direction. And that force is the direction of the electric field. Similarly, if I put a positive charge here, 1 Coulombs, this charge is going to be attracted to that negative charge. And therefore, the electric field is going towards the negative charge. Okay, so this is a sink, this is a source. Okay, similarly, if I try to draw more lines, no matter how I draw, we know that the region closer to the charge will have more lines compared to, or more compact lines compared to further away. The line is much wider. Okay, we know that the magnitude is stronger in this region, and then it's weaker when you go further away from the charge. Okay, so that's how we draw electric field. Simple charge distributions. If we have point charge, we know that that point charge, the electric field is going to point away radially from the point charge. But if we have an infinite long line with a constant charge per unit length, so you can think of this as and this is just looking down here, okay? And then we know that the electric field is going to point radially away from the line. And if you look from the top, it will be in all directions. Again, radially from the cylinder. And that is how the charge distribution for infinite long line of constant charge. And then we use charge per unit length, and normally we use the sign lambda for charge per unit length, and the unit will be coulombs per meter. So point charge, we set coulombs. If you have a length of lines, then we define the charge as per unit length. If it's infinite flat sheets of charge, for example, okay, and we define the charge as per unit area, and then we use the symbol sigma, and the unit will be coulombs per meter. And the charge, no, the electric field will be uniformly perpendicular to the surface, and then pointing away from the surface of the charge. So normal to the plane, i.e. perpendicular to the surface. If it's a spherical, so a sphere, then it's just like your point charge, and that is also radially away from the surface. Again, it's normal to the surface of the sphere. And then if you trace this line back to the center, this looks as if the center is a point charge. Okay, so if I trace all this line back to the center in all three-dimensional, it's eventually go back to a point at the center of the sphere. Okay, so that is the sum of the usual surface that we encounter, or objects that carrying charge, and how the electric field behave on their surface. So in this case here, the electric field is only outside of the sphere. Inside the sphere, there is no electric field. Although I said if you trace back, try to project it, it will project back to the center. I'm not saying that there are electric field inside, but it just project back to the center of the sphere, as if it is a point charge coming from the center of the sphere. Okay, so that is some distribution of usual object, uniform object. The next part we're going to talk about is electric dipole. Okay, di means two. Dipole means two charges of same magnitudes but opposite in polarity. Okay, so we have a positive charge and a negative charge of the same magnitude separated by a distance d. Similarly to your magnets that you know, okay, we have a north and south, and that is your magnetic dipole. Okay, so you have a north pole and a south pole. In magnets, it's always come in a pair. You have a north, you always have a south. Okay, you don't have a monopole magnet. But in electric charge, you can have monopole charge. You can have just a positive charge or a negative charge. Okay, so this is what electric dipole means. I have a positive and a negative charge, same magnitudes but opposite in polarity, separated by a distance d. And based on what we have learned about drawing electric field lines, so we can draw our electric field lines, the E field going away from the positive charge, pointing into the negative charge. And then you can complete that diagram. Further away, the field gets weaker in magnitude. Closer, it gets stronger. And then you can draw the electric field, something like this. Okay, you can also calculate the electric field. So very close to each other, the field is almost the same as that of an isolated charge. Okay, meaning that if I'm very close to here, in this distance here, then okay, if I'm very close to my positive charge, then it looks as if it is a single charge. I mean, if I draw around this line here, it looks as if it's just a positive charge with an electric field pointing away from it. Similarly here, very close, but as you go further, then the charge or the other charge will have an influence on the electric field. But if very close, it's negligible. Okay, so that's what this statement here says. Very close to the charge, it's almost the same as if it is an isolated charge, but further away, it's very different from the individual point charge. So what this means is that the E field here very close, proportional to or your inverse square law. But if you are far away, then this law no longer applies. It doesn't decay with the square of the distance. And we're going to look at that by working out the overall electric field. Okay, so we can calculate this. So we have our negative charge, and then we have our positive charge. We define this distance as d. So if I put our origins here at the middle, okay, so this is my origins. So here will be d over 2, d over 2. This will be my x-axis. At this point here will be plus d over 2. Here will be minus d over 2. So if I want to work out the electric field here, some distance x, then I will have an influence due to a distance. So here will be a distance of x minus d over 2. So this distance here will be x minus d over 2. This distance will be x plus d over 2. Okay, so one charge is sitting at x minus d over 2. And then due to this one, this distance will be x plus d over 2. Okay, so one charge is at x minus d over 2. One charge is at x plus d over 2. And then we can apply our normal equations for electric field. So that will be Q over 4 pi epsilon naught x minus d over 2. That's my positive charge. And then the other one, due to the negative, that will be my negative Q over 4 pi epsilon naught x plus d over 2 squared. Okay, so that's my E field. This is due to the positive, and this is E negative. And then the sum of the two will be this equation here. Okay, that will be working out the electric field at this point here, some point x on the x-axis along my dipole. Okay, I repeat. So let me redraw this. X, this is my origins. I have my positive charge. Or I use plus Q. Let's put plus Q. Okay, I want to work out. So this will be X. So this distance here, there will be, so X is coming from the origin to this point here. Okay, I want to work out what is the distance from this point to X. And this distance here is d over 2. So this distance will be x minus d over 2. Okay, you follow? Okay, so my E field for my plus, that will be Q over 4 pi epsilon naught. My distance will be x minus d over 2 squared. Okay, so that's the electric field due to the positive charge. X origin, here is minus d over 2. That is my negative Q charge sitting. Again, I want to work out at the same x distance. So this distance here is x plus this distance here is d over 2. So the total distance is x plus d over 2 from the negative charge to my x. And therefore, my negative E field, that will be my negative Q over 4 pi epsilon naught. And my distance will be x plus d over 2 squared. Okay, so the total field at x will be the sum of E plus E minus, which is the sum of these two equations here. Okay, sum of this with this. And that will be my equations here. Okay, so Q over 4 pi epsilon naught E minus d over 2 squared minus Q over 4 pi epsilon naught d plus d over 2 squared. What I have done here is I take my x out of my equation. So here is squared. If I take it out, it will be x squared sitting out. And then this will be divided by x. Okay, same thing on this side. And then we can use binomial expansions for this part here. Okay, so 1 minus d over 2 squared. If I do a binomial expansion of that, and that is approximately equals to 1 plus d over x. Okay, so if you expand it, you go further, but the higher terms is very small. Okay, we doesn't need them, so we just take the first two terms. Okay, so that's my binomial expansions for 1 minus d over 2 to the power of minus 2. Minus 2. Okay. And therefore, we can simplify the equations by replacing it with the binomial expansions. So for 1 over d over 2 to the power of minus 2 with 1 plus d over 2, no, d over x. And then for 1 plus d over 2x to the power of minus 2, we can replace that as 1 minus d over 2. Simplify this equation, we end up with this equation here. Okay, so what's the significance of that? Earlier on, we said that next to the charge or close to the charge is decayed by r squared. If you go further, it's decayed by r cubed. So means that if you go further away, the electric field decay much faster at the rate of r cubed or x cubed in this case. And then the q times d, the charge times the distance, separation between them, we call that the electric dipole moment. Okay, so that's the things that I'd like you to grasp from this electric dipole. Okay, so two things to remember. Electric dipole moment is the charge magnitudes times the separation between the dipole moment. Okay, I have minus q plus q and then distance d. So q times d, this is called the dipole moment. And the other things to remember is that the electric field, if I go further away from my dipole, the electric field decay by 1 over x cubed. Okay, so some distance away, the field becomes negligible because it's decaying much faster rate than the point charge. Okay, with that, that's the end of this topic.